Hello everyone. Today, topic of mine is on can large language models reason about program invariants. Let me walk through you all the sections that I'm going to discuss in this topic. So, this is the index. It contains 7 sections. Let us start with introduction. Large language models, as you might know, excel in generating code, but when it comes to analyzing program semantics, challenges arise. Our journey involves leveraging the power of pre-trained large language models to anticipate Java program invariants, opening up new possibilities for program analysis. Now let's break down some key terms. Large language models. These are advanced language models such as ChatGPT-3, designed to understand and generate human-like text. Program invariants. Invariants are conditions that remain true throughout the execution of a program. Think of them as rules that the program follows. Program semantics. This refers to the meaning of the program, emphasizing the understanding of program attributes rather than specific states. Large language models have proven their ability in various domains, showcasing their abilities to grasp the language structures. Leveraging pre-trained large language models offer a promising avenue for tackling the challenges posed by program semantics. Now coming to Java program invariants. Java, a widely used programming language, possesses its own set of challenges and opportunities. Anticipating programs invariant in Java can lead to more robust program analyzing and optimization. Automated identification of program invariants will significantly enhance code quality and performance. Moving to the next slide, we have proposed methodologies. Proposed methodologies. Our strategy revolves around fine-tuning the large language models that have been pre-trained on code to anticipate program invariants. By tailoring these models to specify of Java programming, we aim to enhance their accuracy and adaptability. The key steps in this strategy are instrumentation of Java submission. We start by instrumenting Java submission, incorporating mechanisms that allow us to track program behavior and gather valuable data. Secondly, it is utilizing DICON for dynamic analysis. DICON, a dynamic analysis tool, become a key ally in our strategy. It aids in extracting program invariants from the instrumented code. Dynamic analysis ensure a real-world understanding of how programs behave during execution. Here we will discuss two approaches, direct prediction and scratchpad generation. So let's discuss the direct approach first. To anticipate program invariant, we have crafted a straightforward yet powerful method that focuses on efficiency and precision. By concatenating the source code with the target program point, we create a distinctive representation that captures the essence of the code at a specific location. This allows us to tailor our predictions and specific characteristics, streamlining the analysis and interpretation of the anticipated variants. Unlike some approaches, this method doesn't explicitly consider this sequence of code. Through the scratchpad prediction approach. In scratchpad approach, it is a departure from traditional methods aiming to provide a richer understanding of program invariants. This unique blend captures not only the essence of the code but also guide our approach towards specific location of interest within the program. This structured output provides a comprehensive snapshot of the invariants associated with various segments of the code. Next, we are going to discuss about experimental results. In experiment, the researchers engage with the code context dataset, a vast collection of Java contribution across various programming tasks. This dataset serves as the testing ground for evaluating the effectiveness of our methodologies. The checkered similarity metric allows us to measure the intersection over union of predicted and actual invariant, providing a nuanced understanding of the predictive accuracy of our models. The trio of precision, recall, and F1 score provides a balanced view on the performance of our approaches. Let us discuss through an example of the figure. Here in the figure one, it shows the different strategies for generating input string. We have compared the scratchpad prediction, direct prediction, as well as the Oracle-based dynamic prediction. Scratchpad prediction outperformed the directed prediction, allowing the model to reason about program behavior step by step by predicting invariants at intermediate program points. Interestingly, replacing model predicted intermediate variants with target ones from DICON significantly improved performance, aligning it with the findings on a program induction. Here there are four figures: Jacob distances, precision, recall, and F1 scores that I have discussed. In this figure, first we will discuss about figure A. Here we have compared predicting invariants following the order with an ablation that generated invariant using three randomly shuffled orders of invariant types. The choice of canonical ordering was not found to be significant, emphasizing the flexibility of our approach. Meanwhile, in figure B, it tells us about the effectiveness of mixing prompting strategies. We fine-tune models using combined training samples from three prompt types, such as directed, scratchpad, and Oracle. Combined training appeal helpful for the scratchpad approach, while separated training yield better result for direct and Oracle predictions. Moving to next slide, we have these two figures. Let us discuss the first figure, where we assess the quality of the predicted invariants. We compared our language models with DICON in terms of invariant generation performance. Our approach outperformed DICON when only a small number of traces were available, showcasing the static nature and efficiency of our method during inference. Whereas in the second figure, it tells us about the concept of using backward invariant prediction for test generation. The invariant generated at the start of the program from a set of constraints over program input allow us to select concrete values satisfying these constraints, yielding at concrete test. Now, let us discuss the limitations. In limitations, our approach has showcased robust performance, providing accurate predictions of program invariant. However, it is essential to recognize that even the most effective approach come with some drawbacks. Striking a delicate balance between accuracy and efficiency become imperative. Scalability is a consideration, especially when extending the approach to handle the larger volume of the code submissions. Additionally, the current focus on Java submission leaves an avenue for extension to the other program languages. Moving on to our next slide, we have contributions. So in contribution, the contributors have built up a path that amplifies the precision and recall of the predictions, setting a new standard in program analysis. These models, fine-tuned and honed for program invariant predictions, showcase a level of accuracy that surpasses the traditional methods. By fine-tuning the input directives to guide the large language models, contributors have uncovered nuanced approaches that enhance the interpredictability and relevance of predicted invariants. This exploration expands the toolkit available for the person who are practices in the domain of program analysis. Moving to our next slide, we have future scope. Future holds the potential for models to evolve beyond generic prediction, which envision a scenario where the world can learn specific invariant tailored to downstream tasks. Future endeavors will involve conducting further scalability experiments, exploring how the models perform when faced with even larger volume and variety of code submissions. This analysis is essential for ensuring the practical adaptability and efficiency of the approach on a larger scale. Now, to our last slide, which is conclusion. In conclusion, what output we can take is the approach involves in fine-tuning predefined, pre-trained large language models on coding. enabling them to map from a given source code file and specific program point to a list of predicted invariants. Results indicate the effectiveness of large language models, achieving an impressive 86% of precision and recall, outperforming Daikon when the set of available tests is constrained. This research opened up the path for more accurate and versatile applications of large language models in the domain of the program analysis and the development. Thank you.